A heavy box of weight W slides down a frictionless slope. It's going down. The loss in height is x. Frictionless, so no work is, lost due to friction. It's all being converted into, so the speed gained is all coming from, what do you call this thing? The change in height, so potential energy. What is the work done by the weight W in moving from top to down? So weight W is actually just the conversion of potential energy. It traveled at a height of x. So what is the potential energy that got converted into kinetic energy, right? So that's potential energy. The mass of the object times g of the object times h of the object, right? So none of these quantities are given to us, but we understand from our deep understanding is that mg is essentially weight. So that's w times h, but we don't have h either, but h is given to us as x. So it's just wx. That's the potential energy change from here coming down all the way here, right? It's frictionless, so it doesn't really matter. Anything else doesn't really matter. So that's the work done. That is the work done from converting this energy to kinetic energy, right? So what is the work done by the weight moving the box? It's W times X. And that makes absolute sense because work done is force times the distance the work is force pushes the thing in or whatever, right? So the force is actually W and the distance traveled in the direction of the force is actually X. So this also is giving you W times X. So pretty cool. So the work done by the weight is downwards, and you also realize all of its potential energy due to the lack idealness of the system, the lack of losses, because friction is the only big loss over here. I don't think it's going to lose it any other way. So all of that potential energy is turning into kinetic energy, right? And you can measure all that conversion of energy by, that's the work done, which is also W times X. And there we go. Our correct answer is A. Which change on its own increases the range of a liquid in glass thermometer? You want to change the range, not the sensitivity, the range. So if you have a thermometer, looking closely over here, the difference between these two poorly drawn thermometers is that this is very thin and this is very thick, right? So the mercury inside, let's say in the thin one, let's say you heat it by you warm it up by 10 degrees. You warm it up by 10 degrees. It started at room temperature, 25 degrees Celsius. Now it's 35. So this thermometer, what was that? This thermometer this mercury will expand and so will this. This mercury will expand a lot higher. Like not expand more, but it'll travel a lot more. They'll both expand the same amount if there's the same volume of mercury used. But this one will travel a lot higher because it doesn't have anywhere else to expand except in one direction. That's probably a wrong way of looking at it. It's just that there's just, yeah, it's just common sense. Like, yeah, there's I guess less room is not the right way, but it'll expand more over here in a thinner tube. Why? Or like it'll travel more. Expansion is the same. Say that again. The expansion is the same, but it's going to travel more, right? Because if this expands by, let's say, 10%, it's going to travel a lot more over here. But if this expands by 10%, it won't travel as much because there's a lot more room over here as it moves up. So it can cover this area and doesn't need to travel. Whereas there's very little volume over here. So it has to cover the same amount of volume by traveling more height, right? Because the base has a finite area. Let's go with like pi r square, right? But this area is like very tiny, very small, and the only real gain it can get is by height, because area times height will give you the volume, right? If it's a cylinder, it's going to be pi r square h for the mathy people here. And over here, what's going to happen is that the area is much larger. So even a little increase in height will increase the area, will increase the total volume by a lot, a reasonable amount. So that makes sense. So it can come over here, whereas this will have to travel all the way up to here. So in essence, what it's doing is this is making this thermometer way more sensitive, but this thermometer will start spilling or will break if it goes too high, right? So the range has been decreased because this is like very sensitive thermometer and it travels a lot, but this can travels per temperature is very slow, very low, right? So let's say at, you know, instead of 10, let's make it 30 degrees. This oh, well, 30 is too high. Let's make it 15 even, 15 degrees instead of 10. This will break through this mercury and spill over or break the glass at the top, whatever, while this will stay here and you can use it. So this sort of design will give you a higher range, a longer range, greater range, right? And yeah, so let's see what options will work. Decreasing the length of the capillary, the length will have, sure it'll have effect, but decreasing the thickness of the glass around the tube, you want to increase the range. So increasing the thickness, increase the diameter of the capillary. Capillary is this part. Increase the volume of the liquid in the bulb. Well, yeah, C is our best bet. C. That's our answer. A student is given a thermometer that reads 1 degree Celsius instead of 0 degrees in melting ice and 101 Celsius in pure boiling water. She uses it to measure the temperature of some water before and after it is heated, right? So how does the rise in the temperature of the water calculated from her result compare with the correct value? That's an interesting question. Let's say the actual temperature of the water was actual temperature of the water was, it started off as being not 30, 25 degrees Celsius, and it moved up to 45 degrees Celsius, right? And that's an increase of 20 degrees Celsius. But for the person, the student, measuring this student's temperature, for the student, the reading will say, oh, it's going to be 26 degrees Celsius because it's one higher, and it's an incorrect thermometer, right? And it's going to stop at 46 degrees Celsius. And when she will subtract these two values, she'll also get 20 degrees Celsius. So how do her change in temperature values, or the rise in temperature values, compare with each other? They're the same. They're the same. They're the same. They are the same. The correct answer is B. The critical angle of light traveling from glass into air is 42 degrees. And where does the total internal reflection occur in these two cases? So light's entering over here, and once it enters, it's going to go straight because the critical angle over here is 0, right? The incident angle is 0. So it just goes straight. Over here, if I try to draw the normal, this angle from the normal is 45 degrees. I hope that makes sense. It's 45 degrees and it's greater than your critical angle. So over here, this surface will act as a mirror and total internal reflection will take place, and it's going to shoot it back straight down like that. How cool is that? How interesting is that? It's going to shoot it back right down like that, and it's going to come out just like that. 45, 45. Beautiful. So symmetric, balanced, as all things should be. All right. What about Q? It goes in straight to same principle. It hits here. This angle is 45 degrees, right? this angle is also 45 degrees, and it's gonna hit it like that, and same thing is gonna happen, and it's gonna come right out like that. Interesting, fun stuff, right? And so both P and Q, total internal reflection is taking place. Total internal reflection is taking place in both P and Q. Correct answer is A. What is a typical value for the speed of sound in air? So my memory tells me that it's 330 meters per second. How much that is that in centimeter? I know for a fact that 1 meter is equal to 100 centimeters. So this should be 33000 centimeters. And the second thing is changing, so it's going to be that much. This converted into scientific notation is, the decimal is here. I want to bring it 1, 2, 3, 4. 4 digits to the left, so that's going to be 3.3 times 10 to the 4th centimeter per second. What is that? That is B. Or it would be, because I only saw centimeters, so I tried to convert it. But these are apparently the same values. I just misread it. Because I just saw B earlier. Oh, I was going from bottom when I was looking at values. Thought you had to convert all of them to centimeter. But yeah, this is giving us a good answer. This is what our actual answer is. So answer is not B. Womp, womp, womp. It's actually A. All right. A diode is connected to a series in this manner. What is the trace of the screen? So AC supply over here is trying to shoot an AC signal, which is, let's look at the first half. If this goes through, if this first half goes through, it'll, well, go through, right? And this graph over here will report this signal right like that. Okay, so that's gonna show up. Let's be fancy about it. What about this part of the graph? What's gonna happen? So if this goes through and it's coming, it's gonna stop, right? Actually, when I say this is going through, it's actually going through this side, the reverse. But people like to think of it that, oh, the negative current is going over here, right? So if this is trying to go through, it won't allow it because it's a one-way diode. It only allows positive to go like that, right? So there will be nothing going through over here. So all the negative part of the graph will cut out. Then again, the yellow part comes out because the pink part wasn't allowed to go, right? And yeah, that comes again. So what do we see? What do we see? This thing comes out. Okay. So what is seen at A? Oh, sorry. Oh, yeah. What is seen at our mystery box? It shows us A. The diagram shows the trace on an oscilloscope screen when connected to a DC supply which is being switched on and off. This question is just killing me. The settings of Y, gain control, and time-based control are shown, right? So this is 1 centimeter each block. Each of these blocks are 1 centimeter, right? That's what they're going for. Yep. And they're trying to say, they're trying to say that, okay, these are the settings for the two horizontal and vertical क्या बोलेंगे इनको, gains or whatever, I forgot the knob settings, whatever, Y gain and time base. All right, fine, it's there, right? And this is the cycle. So let's highlight one complete cycle. It starts here, goes like that. Yep, that's one complete wavelength, right? And Supply is on, supply is off. Okay, Y gain, the voltage is, so it's at 2 per centimeter, right? So each is 2, this is 2, and this is 4. So the voltage is, it's trying to tell you is 4 volts, and one cycle of this wave is finishing in 2 of these square, which is 2 centimeters, and the time base is set to 0.01. So that means this is 0.2 seconds, right? So the time period for this wave is 0.02 seconds. So frequency is 1 over time period, and I get this as 50 hertz. That's not bad because that's what you get if you're connected to the supply voltage, right? So it's just literally the supply voltage thing. I'm happy with my answer. So let's check the answer set at the back. Okay, it has to be 4, it has to be 4. And it's 50 and it's 50. Correct answer is C. A body slides down a frictionless slope as shown. Frictionless is important here. Okay. As the body presses on the surface pushes back on the body. Okay. In which direction does the surface push back on this? So they're trying to talk about what is the direction of the reaction force that results from this contact, right? Now, there are multiple ways of doing this. One way of looking at it is that the weight, you have to, everyone's familiar is the weight has to be downwards. And I think a lot of people's intuition is already saying it's C because it's always normal to the surface, right? Let's try to work it out. Let's try to analyze this question more because we have that opportunity right now. All right, so let's say if B was the correct answer. If this was a point where its weight was acting downwards, I'm just converting this rectangle over here to a point mass so we can work with it. And the only reason for that is I don't want to draw a rectangle. If the reaction force was towards the top, if that was a reaction force, let's say it's equal. So that's the same case as a book resting on a table. It's going to be equal, so the book doesn't move at all. There's no movement, right? But if it's not equal, so either the book will break through the table or rise or float away from the table. It's going to go up or going to go down, right? But over here, which direction is it going? It's going here. There is a resultant force over here. So there is some horizontal component over here of some force, right? So let's take a closer look. If this is my weight, again, let's put this part on the other side. If this is my weight, and my resultant force is in this direction. How do I know? Because the direction of motion is that, that's the direction of the acceleration. And acceleration times mass will just give me the force, the resultant force acting on it, which is also acting that way. So let's highlight that resultant force like that, right? Of course, it's going to be, like you can think about it, it's going to be less than the weight. Oops. It's going to be less than the weight, right? So how do I complete this with my reaction force? The only way for me to complete it is bring it here like that, and it makes sense. The system is not in equilibrium because it's falling down. That's why the head and tails aren't matching, right? And that's the resultant force of this block as it falls down. So the reaction force is the only thing preventing it from going down straight, but also adds a component where it's trying to move towards the side a bit. Okay. And yeah, C is our best answer. An object X has a mass m and velocity v. A second object Y has mass 2m and velocity 2v. What are the values of the kinetic energy of Y to the kinetic energy of X? So kinetic energy, so the only reason this question is confusing is it's gonna be kinetic energy KE of y divided by the KE of, well, x. See, I'm already confused. Okay, so kinetic energy of y is going to be half mv square and half mv square for x. And I'll put in the equations here. I haven't filled the variables out. These aren't the same, right? I'm just writing the equation for some help. And we can realize that you can cancel out the half really easily because those are just numbers and you can process them, they won't change. So it's m. What is the mass of y over here? Yeah, y, right? So mass of y is this, and that's, so m has to be 2m, and velocity is 2v, and the whole thing is squared, right? And for x, it's just mv squared. Mass is m and velocity is v, so it's just v squared. So solving this is going to be, this is going to turn into 4, and 4 times 2 is 8. So 8mv squared divided by mv squared. Kachak, 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 kachak. And you have 8 as the answer. Just 8. Sir, answer. Interesting, right? Something going at something which is twice the mass and is going twice as fast as someone else has 8 times the energy. Imagine that. 8 times the energy. Interesting, right? How energy works. Pretty cool. Correct answer is D. All right. A wavefront is essentially how we try to, measure, like this is a wave, right? Let's make a wave. Let's try to understand what a wavefront is. It's interesting. It's kind of almost, and it's common sense, right? Really, right? So what they do is, okay, we gotta talk about how waves, like you're limited to your two-dimensional drawing. Even this is not really how at least sound waves look like, but we try to represent it like this, especially for graphs, right? Oh well. So what they do is, okay, how do I demonstrate the wave? This is just like how the wave is. It's like cross-sectional, right? You're looking into it, right? Like if I want to draw a ball, that's a ball. It's actually a circle, but I mean, we're trying to simplify it. But if I wanted some, depth to it, I tried shading it or something. So how do we add a layer of complexity so we can use this wave understanding and like try to understand it in a different place, right? Like if, for example, if someone's screaming, how is the wave spreading out? So we'll say, oh, how do we, quantify it? Say if someone's shouting, this is what we draw, like these lines. So essentially, what they're trying to say, what these lines are let's say you randomly pick one point on this wave and you highlight it. Like you put a tracer on it, you put a dye on it, color kar diya. You can't really do that, just to picture that for a second. So this is the peak point. Normally that's the case, you'll just do it for the peak point. And in all honesty, you can do it for any point. But that point has to be the same throughout, right? So no matter how long the wave goes, it's gonna look like that, right? Like you're highlighting the peak point. And if there's, and they're like waves are, you can't think of like the same sound wave as many waves, but yeah, so this line is trying to say that the wave coming out is kind of like that. Look how I'm trying to match my peaks, like the top points at these yellow lines, because these yellow lines, this line is highlighting all sets of these peaks showing up, all these crests showing up, right? This is what it says. So looking at this, I know my wave is spreading out. This is what it's trying to say. It's spreading out because, it's not going straight. Like this one is here, this one is going, it's spreading out, kind of like how light does. The other thing is the wavelength is constant over here because the spacing, okay, this is poorly drawn, but it's trying to show that the distance between each peak is the same, so that's essentially one wavelength. So this wavelength is the same, right? That's what we're going for. So let's say if I draw me shouting compared to this random person, and if I draw it like this, what impression are you getting about this? I'm shouting a lot more. What am I doing? You should get the impression that this is probably a shout that is higher in pitch because the wavelengths are lesser. It's closer by. So it's not louder, it's actually closer. And there's no actual good way to declare that it's louder. Maybe you can, add some cartoony effects, which is not canon, to highlight sound key energy or like the amplitude of it. But you're not really highlighting the amplitude, and this just highlights that this is a higher frequency. Normally you don't even use it like that. Oh well, back to this question. Wavefronts from a point source are straight lines. Do they look like straight lines? No, right? Wavefronts from a point source will not be straight lines. So wavefronts from a point source are circular? Well, yeah, I mean, sure. Circular, yes. I'll go with that. Wavefronts are parallel to the direction of the energy movement. That is true, right? So if I try to draw a tangent over here on this wave, it's trying to tell me, okay, it's trying to tell me that the wave is moving like that. And over here, if the wave is moving like that, the tangent is telling me that, hey, yeah, see? So the wavefront are parallel to the direction of energy movement. That's more or less true, right? So they're trying to be parallel. That's why they're spreading out, because the wave is actually, the energy movement is spreading out. Wavefronts are perpendicular to the direction of the energy movement. Oh, it said parallel. I think we mean perpendicular, right? Talking about perpendicular. Okay. Yeah, this is perpendicular, not parallel. I'm just confusing the words up. Which two statements are correct? And I think we highlighted with 2 and 4. 2 and 4, which is D. A man stands 80 meters from a foot of the cliff. Wow. 80 meters. He makes a loud bang and listens for the echo. All right. He makes a loud bang once every second. So he's an idiot. He hears an echo exactly halfway between the bang that caused it and the next bang. So he heard the echo at 0.5 seconds. Isn't that what it's trying to say? 0.5 seconds. Why? Because he heard it between the next bang and the bang that caused it. So the echo came, he was about to make the next bang, right? Like, so the next bang would have come 1 second later as soon as he, triggered it. But he heard the echo between the two sounds, exactly in between, so it's half. Okay. So that's the time and that's the distance traveled, because the sound is coming back and forth, and the distance is actually, traveled distance is actually 160 meters. And what is the speed of sound? Brilliant question. Speed of sound is velocity, 160 meters, that's how it traveled, and it's 0.5, so it's double that, 320 seconds. Meters per second, right? Meter per second, look at that. That's our answer, D.